Hello everyone. I would like to talk about self-similarity matrices here and to go over again what we did in class so you have a reference, and then to take it a little bit further and show you some computationally efficient ways to deal with self-similarity matrices. So first, we're going to be looking at self-similarity matrices on chromograms in this example. It's a more general idea, but the chromograms end up working well for the application of different versions of the same tune, or sometimes called cover songs. So that's what we'll start with. And the reason is because the notes don't change between cover versions generally. Now, I spent half of my dissertation talking about where this breaks down, because some tunes don't even have notes in them, or the notes don't carry the dominant musical expression. But this is what most people had done before me, and so I'll focus on that for now. Okay, so as you recall, we did this out before manually, but the chromogram is what you get when you apply a filter bank, where there's a little bump over every place, every octave that has a particular note number. So we get the strength of the 12 note numbers over time. So we've really compressed the spectrogram just to 12 rows, where each row is a different pitch class, is called, or just the same note number but in different octaves. So for example, A would be note number 0, 12, 24, but also negative 12, negative 24, etc. And so anyway, here is the chromogram that we get from Michael Jackson's Smooth Criminal. Now what we see actually is some repeating patterns. This is the interesting thing that we're going to think about now. So we see a little bit of music structure here. And so we might say that, for example, it looks like this little section here repeats itself perhaps here and also here. And it also looks like we have a section here repeating itself here and here. And so those are just a couple of examples. And also we happen to have an intro here, which is a little bit different from everything else. So interesting what you can already see just from these chromograms. Actually, if I take a cover song of this, so by Alien Ant Farm, so a different version, I see actually remarkably similar patterns. Too similar. I meant to plot this other one. Okay, here we go. Okay, so not exactly the same, but we see some of the same kind of repeating patterns over time. So that's kind of a sneak preview of why these might be useful for versions. Now, I just wanted to show one more example and actually play a clip from it of two other versions. This is of the song Abracadabra. I'm going to reach out and grab you. So the original version was by Steve Miller Band. So if I play that. Okay, so that's enough for you to get the idea. And then here's the cover by this Sugar Ray, if anybody remembers them. So remarkably similar, but if you were paying close attention, you'll notice that the Sugar Ray version was down by one half step. So what you see here is, like, for example, if I look at the note number A here, I see this kind of pattern. I see a similar pattern, but actually one half step below A. So what's happened is we've circularly shifted the chroma that's up here down here. So everything moved down by one, and then actually the bottom row moved to be the top row in the Sugar Ray one. So anyway, that's just to tell you how we can use chromograms for audio similarity. But I want to introduce another tool, which is a kind of a different representation of audio that can be used not just on chroma, but also on things like MEL spectrograms, which also factors out specifics about, you know, timbre or whatever the feature is. It factors out the specifics, but is more about relative patterns over time. So this is called the self-similarity matrix. And it's defined as a matrix that has as many rows as there are columns in whatever feature spectrogram that you're looking at. So I will naively make a method that implements this. I'll say, okay, n, or maybe m is the number of columns. So I'll say x.shape1. And this is a matrix that has m rows and n columns. And every element of the matrix, so I'll loop through every single element of the matrix. Every element of the matrix is a similarity between the column at time I and the column at time j. When we're using chromograms, we're going to use a particular kind of similarity called the cosine similarity, which is defined this way. So what it is, it's the dot product between two columns, but after we've divided the columns by their magnitude or norm. So just to show you, okay, let's say I pull out, I'll call it xi, that would be column I here. And so the way that I would normalize this is by dividing it by the square root of the sum of the squared elements of this. That's what this means. This absolute value or norm of this column. So I'm going to divide the column by the sum of the squares of the elements. And what this really is doing, this is kind of like a loudness normalization. So this is like saying, okay, it doesn't matter how loud this was, because I could have the same notes, but they would be 10 times louder. So all the features would be, all the dimensions would be 10 times in magnitude. But I'm going to factor all that out, okay? And so I'll do the same thing with the jth column. So this is one way you can normalize them. And then what I'll do is I will fill in row I, column j with the dot product. So I'll just do sum of xi times xj. So this is exactly like the dot products that we were doing when we introduced the discrete Fourier transform. Okay, so let me just, before I worry too much about what the heck I'm doing here, let me just run this. And actually, I want to run this on, let's see, I called it chroma up here. I'll run this on the chromogram for the Michael Jackson Smooth Criminal. Still having an issue here. It says n is not defined. Where did I use n? Oops, I meant to say mm. Okay, there we go. And finally, it says xj reference before assignment. I meant to actually pull xj out of the column. There we go. Okay. So this is computing the thing. Now it's taking quite a long time actually. This is not the way we want to do it in practice. We can actually write this much more efficiently if we exploit matrix multiplication, because matrix multiplication is doing what this is doing up here. So actually maybe I'll keep this in view, but I'll work on the other version that's faster. So what I will do is notice that, okay, I'm doing the dot product between every column of this x with every other column of x. And if I rearrange things a little bit, I can see this is a matrix multiplication. Okay, actually this visual is going to help us a little more to understand this. So let's say that the chroma matrix looks like this. So we have all these columns, x1, x2, and x3. So that is the chroma matrix. I will call it C for now. If we take this matrix and we copy it, but then we transpose it, so that's flipping the, that's treating every column as a row. So this, remember, this is actually called C transpose. So I'll say C.T because that's how you would access it in NumPy. And so if I do the multiplication C transpose times C, the matrix multiplication now, then I'll be doing all the dot products that I wanted to do, right? So like element and row, the first row, first column would be the dot product of the first column with itself. The element of the first row, second column would be the dot product of the first column with the second column. And so this is a much better way to write this out. So what we can do actually is say, all right, I'm actually going to make a D. Well, first I should actually normalize all of the columns. So I'll say maybe x norm is equal to x over square root actually, okay, let's compute the norm of each column first. So I'll say that is square root of the sum of x squared. I'll sum down the rows. And then what I'll do is I'll divide x by the norm. Okay, so this is just setting it up. So this step, the code's a little weird here, but just normalize each column in the same way. This normalizes them all in one shot using some NumPy magic. And then the self-similarity matrix is as simple as just saying, okay, it's X transpose, or I guess I called it C here. But yes, let me actually, I'll be consistent here and call this C. So it's just the matrix multiplication of X transpose with X. All right, so if I look at that, say D is equal to get SSM chroma. Let's have a look at that. Gotta make sure I miss a spot there. So there we go. Okay, this computed much faster, and here's what we see. And so as I was pointing out in class, what used to be, we would look at the chromogram and say, okay, I have these repeated sections. They turn into blocks in this matrix. So when you're within one section, so if I throw on the color bar here, and let me actually get the scale right here. I'm going to say Vmax equals 1. I guess that washed it out a little bit. Okay, we'll keep it what it was. But yeah, if I throw on the color bar here, so the most similar ones are a similarity of 1. That would be everything along the diagonal. So a column is the most similar to itself than it is to anything else. But even some off-diagonal things are pretty strong. So what that's indicating is everything that occurred a little bit later here, so around 2000, is also similar to everything around 1000. That's because I'm in the same section. Okay. Now, but one thing that's a bit cumbersome about this, and maybe not the best idea, is that the columns that we're comparing capture very small snippets of audio. Every column is just one window of the spectrogram. It's actually remarkable that it looks so clean. A single window of the spectrogram could be a little bit noisy. And so oftentimes what we do is we average together a bunch of chunks. So what I'll do is I'll take maybe every 40 columns and replace them with just a single column, which is the mean of those 40. So I'll call this chunk average, and then I'll say maybe size, whatever that's going to be. That'll be the size of a chunk. So replace a chromogram C with a chromogram dash where we replace each size, or I guess I said F here. Replace each chunk of F columns by the average. Okay, so what I'll do here is I'll just say, maybe I'll call it C2, and I'll say that's zeros. Okay, it still has 12 rows, but I will only give it as many columns as there are columns in C, floor divided by F. And so now I'll simply loop through. I'll say, okay, I in range C2.shape1, so as many columns as there are in C2, and I will make the let me call this J. I will make the jth column of C2 be the mean of F contiguous columns in the original one. So I'll say, okay, maybe J times F up to J plus 1 times F. And I'm taking the mean of the column, so I'll say axis equals 1. Sometimes people do the median. That's also not a bad idea because that can get rid of some outliers there. But I'll do this here. So I'll do something similar, but I will actually do the self-similarity matrix on the chunk averaged chroma. And let's say that maybe I average every 40 columns together. Okay, so this is a little bit more, let's do a little bit of analysis of this image and see if we can understand what the different blocks are. So to do that, I'm going to have to convert the units of index here into units of time. And so actually, let me define a variable for f. Let's say f is 40. And so what I can find out here is that, okay, every window advances by a hop length of hop. And now we're averaging 40 windows together. So actually, the number of samples that a single row takes up here, or a single column equivalently, it should be f times the hop length. And so actually, let's actually just divide that by the sample rate. And so every row takes up about a second of audio. Not quite a second. Let's see if we can get that a little closer here. So if I average together maybe 50, okay, I overshot it there. Let's say 45. Now I'm darn close. Let's see. Okay, 43. Each one of these is about a second now. That's pretty close. Okay, so the hop length times how many I'm averaging together, divided by the sample length. Okay, so if I look at this, I see, and I'll put this into Matplotlib interactive mode, so I can actually see here exactly where I am. All right, so let's look. So we have a block here at the beginning, and so that ends at around 50, or let's see. Let me zoom in a little bit here. That ends at around, 14, 15 seconds. So what is that? So here is that tune. And actually, that's the end of the intro. So the first block is the intro. That's its own little section here. It's not really similar to anything else. So we see every other column is not very similar. Okay, now this block here goes until about 45 seconds. So the thing starts off, and we say some stuff. And then we transition. Okay, so between, so that, let's see, it was a little bit more than 45 seconds. So between like 47 seconds and 63 seconds, it looks like there's another block. So let's see. So we're getting about, and there we go. Now we're in another section, so I actually see a different block here. And then I repeat myself again. I go back to the whole, and are you okay thing at around 80 seconds again. So that would be a minute 20. So if I jump over to a minute 20 here, back actually, so that was the end of the chorus, so right before. So that's why I actually see that this block is similar to this block here, right? So you could see quite a lot about the structure. Okay, there's one more thing I want to do to enhance this matrix, and it's probably easier to explain with a picture first, and then I'll dive into the math. So what I'm going to do here is replace each pixel by the average of that pixel and a few pixels that follow it. So when I say here k is equal to 4, I'm going to replace a pixel by the mean of that pixel and the 3 pixels that come after it along the diagonal that it belongs to. And what this does is it enhances the diagonals that are in this image. And what it does is it makes a particular structure pop out here. And actually it's easiest if I show you this interactively. Here's another similarity matrix that I made in a very fancy way in a paper that I wrote a couple years ago. And so what a diagonal indicates, so I see a pretty long diagonal here. So a long diagonal indicates that there is a big chunk of audio that repeats itself in sequence later on. So what I'm finding here is, okay, the diagonal that starts here, I'm saying column J here is similar to column I, but so is column J plus 1. being similar to column I plus 1, and column j plus 2 is similar to column I plus 2, and column j plus 3 is similar to column I plus 3, and so on and so forth. So that's telling me that an entire sequence starting at j, at column j, is similar to an entire sequence starting at column I. So let's hear what that sounds like. So now what I'm going to do is okay, I'm going to jump between the diagonals. Now let me jump back over here. So that sounded like a pretty nice transition, right? But I actually just jumped back in the audio. And let me jump forward again to this diagonal here. Alright. So the diagonals tell me an entire chunk that's repeating itself. So let's see if we can't enhance those in code. So what I will do first is just kind of the brute force approach, which is for each pixel, I'm going to replace it by the average of what was at that pixel and the few pixels that follow it. So again, if column I is similar to column j, and these are each the beginning of a whole section that's similar, then it's also true that column I plus k will be similar to column j plus k. And so when I sum them together and average them, I'll get a very high average if they happen to be on a diagonal. If they're not actually on a diagonal, then the averages may be lower. Some pixels will cancel each other out. And so the diagonals will become more distinct. So you see how there's a higher contrast now between the diagonals and some of the blocks. So this is kind of the brute force definition, and here's the result when I look at it. That was k equals 9. Let me go back. Actually, I found that k equals 4 looks a little better here. So I'll do k equals 4. Okay, so there we have it. But I want to show you a way to do this that is faster in code, because this is a bit of a bummer computationally. It's going to take time proportional to the number of rows times the number of columns, so that's m times k. And so that would be 4 times m times m here. But it's actually possible to do this in just time m times m, so k times faster. But I have to use a little trick about cumulative sums down diagonals. And this is similar to a trick I used much earlier in the course when we were looking at zero crossings, if you remember that. But so here's the idea. What I can do is take out a diagonal from the matrix. There is a command to do this in NumPy called np.diag. So, all right, so I'm working with this matrix D here. And so I will take out, let's say, first diagonal 0. So that's the diagonal that starts here. So it's actually indexed by the columns that it's part of. So the column that it starts at. So the diagonal that starts at column 0 is the main diagonal. And if I plot that, I get a straight line at 1. And that makes sense because the main diagonal is the most similar you can possibly be. Every column is similar to itself with a similarity of 1, right? If I go back and look up at the color bar here, every column is similar to itself with a similarity of 1. So that's the main diagonal here. Let's look at the next diagonal, the one that starts at column 1, just right after that and goes down. And this one is a little bit more interesting. And let me go even a little bit more ahead that. Let's try to find, so this diagonal, this bigger one, maybe that starts at around column 50. I don't know. I'll pull out column 50 here. Okay. So these are a little bit noisy. What we can do is actually do that averaging. And if I were going to do this exactly how I did before, I would say, D2 is equal to np.zero's length of D minus k plus 1. So again, my k is going to be how many pixels I'm averaging together. And so if I were doing this just like I did before, well, I would make D2 at index I be the mean of this diagonal from I to I plus k, right? And so let me plot D2 next to D. Okay, so here's what we see. So here's the original in blue, and here's the diagonal average in orange. So you can see we're smoothing out some variations, right? But there's a quicker way to do this with a cumulative sum. So what I can do actually is, so this is the slow way, but I can actually say, let me make this cumulative sum, which, well, I guess I'll call it dsum. And I'm going to cumulatively sum, so this is like integrating but numerically, this d. And then I'm going to make d2 equal to dsum from k to the end minus dsum from 0 negative k. And actually one more thing I got to do here, I have to add a 0 to the beginning. This is a bit annoying. So one thing I have to do is if, for the dimensions to work out here, I have to add a 0 to the beginning of this. So first I'll say d is equal to np.concatenate 0d. Okay. Now I should have it. Oh, and of course, okay, I'm summing, but I have to divide by k in order to get the average. All right, so let's do that. Okay, so this is this cumulative something I did, which this is actually equivalent to an average. I explained that on a previous. Okay, just to remind you, I've already talked about why sliding window averages or sliding window sums can be computed using a cumulative sum much more efficiently. So if you go back to Module 5, I explained how this works on counting 0 crossings in a window that's sliding along. And so we could just take out every window manually, all the samples in the window, and compute the sum or compute the average in our example. But it's much faster to do with a cumulative sum. So I'll leave you to go look back at this module to review how that works. But for now, I'll just take it as a given. And what I would like to do is apply the trick that I just showed to every diagonal in the matrix. Okay? So rather than looping through every pixel, I want to loop through every diagonal of D. And I'm going to take out each diagonal, do the cumulative sum, and then put the resulting diagonal into my result matrix. Okay, so what I'm going to do first is, so I was messing around a little bit with the diagonals here. And so I showed that, okay, this command called mp.diag allows you to extract a particular diagonal. And so 0 is the main diagonal, a positive number is a diagonal in the upper triangle here, and a negative number is a diagonal in the lower triangle. So the diagonal that we start off with would actually be negative m plus 1. That would be, that's what we would index it, where m is the number of rows. And the diagonal that we end it with would be m minus 1. So let me start off here just setting up the loop for the diagonal. So I'll say, okay, for diag in range, I'll say negative m plus 1 up to m. So this will go from negative m plus 1, which is the lower left diagonal, to m minus 1, which is the upper right diagonal. Okay, so that's going to go through all the diagonals. We should also, it's going to be very helpful if we also keep track of the row and the column where the diagonal starts. So the lower left diagonal starts at row m minus 1, column 0. So I'll say I starts at row m minus 1, column 0. And eventually it's going to end at row 0, column m minus 1. Okay. And so as I'm going through this loop, let me also increment where the diagonal starts. So if I'm below the main diagonal, what I want to be doing is actually decrementing I. So I still start at column 0, but I'm moving my I up. As soon as I get to I equals 0, I switch to the upper triangle, and I keep I fixed at 0, and I start to increment j for the diagonal that I start off. So I guess what I'll do is I'll say, okay, if I is 0, that means that I've reached the main diagonal. I will increment j. Otherwise, I haven't reached, so this is I'm in the upper triangle. Move to the next column to start off at. Otherwise, I'm still in the lower triangle. and I need to move the start up one row. So in that case, I'll say I0 minus 1. Okay, so that should move me along the diagonals. And now I just need to take this little experimental code that I had. And so what I'll do is I'll extract the diagonal from this matrix. And then I will do the cumulative sum. So we extract, extract diagonal from matrix, perform cumulative sum, averaging. So I'll say, should say perform fast cumulative sum averaging. And now we have to put this result into the resulting matrix. So put result D2 into the matrix, into the appropriate diagonal in the matrix S. Now here's where I'm going to do kind of a weird slice assignment. What I want to say is this entire diagonal, starting at row A and going for as many pixels as there are in this average diagonal D2, and starting in column J and going for that many pixels is equal to D2. So that's kind of a weird slice assignment because I'm actually slicing out a bunch of elements in a row, and then in parallel I'm slicing out a bunch of elements in a column. So this is a way to slice out a diagonal in a matrix. Okay, now did I get this right? So I'm saying I want to slice out this diagonal and assign to it the result of doing this cumulative sum. Okay, let's see if that worked at all. So do I get the same result here if I go ahead and do this? Oh, it says local variable dereference before assignment. Oh, I should have said was that. Okay, good. Woo, I got it. Nice. Okay, so this is a really fast way to do it. And if I were to make k to be something extreme, 100, this is too much. But, well, I don't know, maybe. I can definitely clearly see, where a repetition is. But anyway, if I dial this up to something extreme, it takes the same amount of time. So it does not scale with k. That's a very powerful thing here. And it's also, you're going to do a similar trick in the let it be assignment, and this is a much faster way to do it. All right, so I just wanted to go through all that, and hopefully that makes sense. And so I'll continue on in a moment and explain other things that we can do with these matrices.